Hi, I'm Alex Mitrevski, PhD student at RWTH Aachen and Hochschule Bonn-Rhein-Sieg in Germany, and I would like to present our IROS 2021 paper titled Ontology-Assisted Generalisation of Robot Action Execution Knowledge, which is joint work with my PhD advisors, Professor Plöger and Professor Gerhard Lakemeyer. Our overall work revolves around the problem of robot execution failures and aims at developing methods for analyzing and avoiding those. Failures are particularly likely when a robot needs to generalize its action execution knowledge, for example, when grasping new objects. In the example shown here, the robot knows how to grasp some objects, such as a pitcher, a banana, and a tennis ball, and it now has to grasp a baseball, which is an object that it hasn't grasped before. This is a very simple case in which execution knowledge generalization is required. One way in which knowledge can be represented and which allows generalization through automatic inference is using an object ontology. However, ontology is usually model static knowledge, which would lead to repeating incorrect generalization decisions. Data-driven methods are much more popular for learning flexible action execution policies based on sensory inputs, particularly using neural networks, such that they rely on a network's ability to interpolate between inputs for producing appropriate execution parameters. This works quite well in many cases, but makes it difficult to analyze generalization failures, which is important when robots are used in human-centered applications. We believe that an intelligent generalization strategy would be somewhere in between these two seemingly distinct paradigms. Namely, a robot should be able to utilize both prior knowledge and its own experiences in order to guide its generalization, but should also be able to realize that its current knowledge is sometimes insufficient and additional learning is required for better action execution. In this paper, we study the problem of how to generalize execution knowledge when performing different actions, for example, object grasping, with objects that are potentially known to the robot, but which have not been manipulated before. We particularly propose a probabilistic method that uses an object ontology as prior knowledge for guiding a robot's generalization decisions, such that this knowledge is refined by the robot's own generalization experiences. Our overall objective is to create a representation that leads to explainable generalization, which can directly incorporate human feedback and which can be used for lifelong acquisition of execution knowledge. For guiding the process of action execution in this work, we use execution models of parameterized actions, which we presented at last year's IROS. An execution model example is shown in the figure on the slide. An execution model of this type consists of two components. The first component is a relational model that defines qualitative conditions under which an action succeeds. If the action is performed under multiple qualitative modes, the relational model is actually a set of relational models. The second component is a Gaussian process that maps action parameters and potential execution constraints to a numerical value that represents the predicted execution success given the parameters. An execution model will usually be learned with one object class or a small set of classes. In this paper, when we refer to model generalization, we mean using a model that we know can be used to execute an action for an object class O for executing the same action with another object class O prime. The second important concept behind our work is that of an object ontology. An object ontology can be defined as a tuple that consists of two elements: the T box, which contains object class definitions, object property definitions, as well as relations between object classes, and the A box, which includes object class assertions and property assertions. For concreteness, we assume that we have an ontology in the web ontology language, or OWL, and that the class hierarchy in the ontology is static. In this paper, we only deal with generalization over the classes in the T box. An extension of our method to the A box is possible, but with a considerably higher computational cost. The ontology-assisted generalization method that we present in this paper is based on the notion of a suitability graph. Given an object O, we define a suitability graph as a probabilistic model over objects related to O in an ontology, such that the model essentially encodes how suitable the models of the related objects are for executing the action with O. This is illustrated in the example shown here, which is a continuation of the example we saw a few slides ago. If you want to grasp the baseball, the known models of the pitcher and the banana should not be considered for generalization, as these objects are not related to the baseball. Among the related objects, the model of a tennis ball is more likely to be more suitable than that of a rugby ball, as the baseball and the tennis ball are more similar to each other. This is what the suitability graph aims to represent. The notion of related objects is represented through an object cluster, which is defined on the graph induced by the ontology hierarchy. In particular, given an object class O, we define an object cluster as the set of ancestors, siblings, and children of O in the ontology, for which an execution model is already known. Classes for which an execution model is not known are not in the cluster because the robot doesn't know how to perform the action with those either. Here we see a very simple example of an ontology encoding kitchen object categories. For the class spoon, the object cluster will consist of the classes marked by the green edges, but the kitchen utensil category will not be included in this case because an execution model is not known for it. The object cluster includes all related object categories for which action execution models are known, but these are likely not all equally applicable for executing an action with the object of interest. The applicability of different objects is modeled by a suitability graph, which represents a weighted probability distribution over the objects in the object cluster. The format of the distribution is shown on this slide. The distribution encodes the robot's belief that the model of an object class O tilde is applicable for executing a given action with an object of class O, such that this belief is recursively updated as the robot attempts model generalizations. Essentially, the distribution balances the similarity between object classes in the ontology, which is used as a weighting factor, and the robot's own generalization experiences, which are encoded through a success probability distribution. To find the similarity between classes in an ontology, we use the Wu-Palmer similarity, which is defined as a ratio of class depths, namely the depth of the least common subsumer of the classes O and O tilde, which is the most specific common parent in the ontology, and the sum of the depths of O and O tilde. This similarity measure has properties that correspond quite well to the suitability graph. First of all, the measure considers sibling classes to be more similar to each other than classes at different levels of the hierarchy, which puts an intuitive prior preference on sibling classes. The similarity also increases as the depths of O and O tilde increase, which means that when the ontology model is more specific, the similarity between classes is also larger. We represent the robot's own generalization experiences by a success distribution, which is modeled as a sequence of Bernoulli trials with an unknown success probability. For this purpose, we use a beta distribution as a model. The beta distribution is defined by two parameters, alpha and beta, whose posterior form, which is shown on the slide, depends on the generalization successes and failures. During the computation of suitabilities, the success probability is estimated based on the current values of alpha and beta, such that it should be noted that these parameters are updated separately for each object category in the object cluster. To represent the fact that the robot is initially ignorant about the probability that using the model of object class O tilde will lead to execution success, we set the initial values of alpha and beta to be equal. Given the object cluster and having computed the suitabilities, the model to be generalized is the one belonging to the object class for which the posterior suitability is the highest. At this point, it is interesting to shortly consider how the suitabilities will evolve over time. In particular, before the robot has collected its own generalization experiences, the suitabilities are dominated by the class similarity in the object ontology. However, as the robot collects more generalization experiences over time, the suitabilities will be dominated by the outcomes of the generalization trials. The algorithm shown on this slide simply summarizes the process of selecting a model for executing an action for an object of class O. In particular, if a model for class O is already known, O's model is directly selected and there is no need for generalization. If this is not the case, the suitability values are calculated based on the object ontology and the collected generalization experiences, and the model belonging to the class with the highest suitability is selected for generalization. It can be noted that as a robot attempts model generalizations between object classes, it will continuously acquire evidence about the cases in which particular models are or are not applicable. Based on this evidence, certain conclusions can be drawn. If the model of a given object class leads to successful execution for all sibling classes, we can conclude that the model is applicable to the immediate parent class. We call this a generalization heuristic. If, on the other hand, the failure probability is larger than a given threshold for all classes in the object cluster, none of the existing models are applicable for the object of interest, and a new execution model needs to be acquired. We refer to this as a specification heuristic. We analyze our proposed ontology-assisted generalization method by performing experiments with two actions, namely grasping an object and stowing an object in a drawer, both with a Toyota human support robot. For both actions, we performed experiments with objects belonging to categories in the YCB object dataset, though it should be noted that we used local objects that closely resemble the objects in the dataset. For the experiments, we learned models for 5 objects by performing 25 learning trials per object. Generalization trials are then performed with the remaining 10 objects, such that we performed 10 generalization trials per object. The outcomes of all trials are labeled manually. The objective of the experiment was to experimentally verify that the learned models can indeed be generalized to objects that have not been manipulated before, but also to see how the temporal nature of the suitabilities leads to adaptive generalization behavior by the robot. Our experimental data and an implementation of the generalization procedure are available via the provided links. In order to keep the grasping experiment at a manageable level, we only allowed sideways grasps, such that we parameterize the grasping action by the gripper's offset from the center of the object's bounding box and the orientation of the wrist relative to the object's orientation. Here we learned dedicated object models for a Pringles can, a tennis ball, a sugar box, a cup, and an apple, and then attempted generalization of the models based on an object ontology that includes the experimental objects and various other common domestic objects. We model the stowing action by the position at which the robot releases the object, which is calculated relative to the bounding box of the drawer, as well as the wrist orientation at which the object is released. Stowing models are learned for the same objects as in the grasping experiments, and the remaining objects are then used for the generalization trials. We show a small subset of the results on this slide. A detailed discussion of all results is included in the paper. For some of the objects, the object cluster only contained a single object, but for objects such as the cracker box in the picture, 2 models were applicable, the model of the Pringles can and the model of the sugar box. Here, it is interesting to note that the model of the apple is expectedly not useful when grasping a banana due to the difference in shapes, but is applicable in the stowing case. As expected, the model of the tennis ball can be generalized to the baseball for both actions. The wine glass can be grasped using the model of the mug, but this model is not useful for the stowing action as the glass is a delicate object. Finally, the elongated cracker box and pitcher could not be grasped reliably with the existing models, but the sugar box model was generalized to both objects in the stowing case. In conclusion, in this paper and with our experiments, we have shown that by combining a structured knowledge base that serves as prior knowledge with a robot's own generalization trials, even fragmented and seemingly incomplete execution knowledge can be generalized when executing actions with objects that have not been manipulated before. This is possible primarily because the generalization behavior can be continuously adjusted based on the outcomes of the generalization trials, which represents a form of lifelong learning. Additionally, with the proposed generalization heuristics, it is possible to conclude whether the existing knowledge suffices for execution or whether additional learning trials have to be performed. Despite these promising results, there are various aspects that future work needs to address. One desired extension of the proposed method is that of allowing new object classes to be added to the object ontology throughout a robot's lifetime. A related question that needs to be addressed is that of how to adjust the learned suitabilities if a new execution model is learned for a class that is related, since in this case, the robot doesn't have information about the applicability of the new model for the object of interest. Another useful extension would be that of including object affordances in the definition of an object cluster, as affordances would constitute even stronger prior knowledge that could guide the generalization better. As was shown in our experiments, our method is not action specific and is equally applicable to all object-centric actions that a robot may need to perform, but it would still be useful to perform a direct comparison with some action-specific methods. Finally, it would be interesting to study whether generalization knowledge can be reliably transferred between actions, as different objects will often be manipulated similarly regardless of the action that is performed. Thanks for your attention.